These are the notes for Unit 5, Day 5, and they start on page 13 in your packet. And what we're talking about today is using something called the candidates test to determine global extrema. So remember, global is the biggest of the big or the littlest of the little. That's what extrema is. And so another word for that is absolute extrema. So our essential question is, how can I use the candidates test to identify and, it's a big and, justify the locations of those global maxima and global minima? And so in order to talk about those global extrema in a general sense, we need to talk again about the extreme value theorem. Right, our extreme value theorem says a function that is continuous on a closed interval. So in other words, we have to have a defined interval that has endpoints, must assume a global maximum and a global minimum over that interval. So if it's going to be closed off, we know that there's the biggest of the big and the littlest of the little. Those extreme values can only occur at the endpoints of the interval or at the interior critical points. So it's got to be one of those two types of locations. Okay, so how is this relating to the candidates test? Okay, so the statement here, since there must be a maximum and a minimum value on a closed interval where the function is continuous, to find them, we need only search these locations where they occur. Okay, so let's think about, a general function with closed endpoints. Okay, those global maxima and global minima are either going to be at the top of hills or the bottom of valleys. Okay, or the top of a cusp or a corner, or the bottom of a cusp or a corner, or at the endpoints. Maybe one endpoint is way up here, or maybe one endpoint is way down here. So it's going to be those locations. So we're talking about hills and valleys, cusps and corners. Those are all continuous functions, and then endpoints. So locations are endpoints of the interval or interior critical points. We call these candidates. So those locations we call candidates. In other words, we're going to find them because we have a process to find them. Right? We have a process to find where a max and a min is, even if it's not defined like a cusp or a corner. Right? Maxes and mins, hills and valleys, derivative is equal to 0. Cusps and corners, derivative is undefined. And then we know the endpoints because we know the defined interval. Okay, all of those are called candidates. In other words, it's a potential that they're going to be a global max or a global min. That's why we call them candidates. Okay, so things to kind of highlight here, extreme value theorems coming into play again. Extreme values means we want function values. That's what we're looking at evaluating. Must be a continuous and on a closed interval, continuous function on a closed interval. Extreme values are occurring at the endpoints or the critical points. So that's what I was just kind of commenting, either the endpoints or the critical points are those hills, valleys, cusps, and corners. And we call them candidates. Okay, so the following steps apply to a continuous function. Functions extrema can only occur at critical points and endpoints. So it behooves us, of course, to find those critical points. So notice we're coming back to that skill of locating critical points. We're coming back to, I need the derivative. Maybe I need to differentiate something. Maybe I already have it. I need the derivative. I need to set it equal to 0. I need to factor and solve it. And then I need to look at that derivative and say, is it undefined anywhere? Those will find our hills and valleys and our cusps and our corners. We list them in a table. Okay, so we are literally going to make a table. We're going to list all of those hills, valleys, cusps, corners, endpoints, all of the x values. And then we're going and plug all those x values in and find all the y values. And then we're just going to take the biggest of the big and the littlest of the little. And those are going to be our extrema, our absolute maxes and our absolute min. So let's take a look at this just from a graphical standpoint. Example 1 here, f of x is decreasing and are continuous over the interval -3 to 5. So here's -3 to 5. Notice it's decreasing, right? Decreasing, we know, means that the function values are getting smaller. We also know decreasing by the fact that the derivative is negative, right? All of the slopes of the tangent lines are negative. It says, where does the global maximum occur and where does the global minimum occur and what are their values? Okay, so we wouldn't even need a picture per se, but I just want to start out with a graphical picture because we have this description here. F of x is decreasing over a continuous function, decreasing and a continuous function. That means the derivative, like I said, the derivative is less than 0. Okay, and so even without this graph, we can determine what the answer is. So we know the global maximum then is the left endpoint. Okay, it's going to start high and go low. Okay, so the left endpoint is the global maximum since the derivative is less than 0 on the interval -3 of 5. So we can determine where the global maximum is, and then here's our justification. Because the derivative is less than 0 over the entire interval. And then likewise, the global minimum's got to be the right endpoint for the same reason. Okay, here's the same justification because our derivative is less than 0 on that interval from -3 to 5. So when we talk about making justifications, we're talking about really referencing that derivative, whether it's positive or negative or 0 or undefined. Okay, so what are their values? Well, the global maximum, we're going to have to read off of the f of x axis, the y-axis. And it looks like, let's see, 1, 2, maybe that global maximum is somewhere about 1.5. And the global minimum, we're going to have to, again, read off the axis. It looks like it's maybe just a little smaller than -2, so maybe -2.25. So that would be their values, approximately. Let's take a look at number 2. It says f of x is a continuous function over the interval -3 to 5. And the derivative is positive, right? Greater than 0 is positive from -3 to 2. So the domain from -3 to 2, we have a positive derivative. Okay, and I'm not quite sure why a period is there, but and the derivative is negative from 2 to 5. What extrema is found on the interior of the domain? Okay, so whenever, we don't have a picture along with the statement, which is okay. We can work with what the derivatives are on these intervals to answer the question. But my recommendation is that you draw a sketch. And the sketch is kind of like your derivative number line, so to speak. So it can't be used as a justification, but it's an organizer. So it helps you form the statement for your justification. So let's go ahead and get a sketch of this. So we know that a positive derivative means the function is increasing. So, and we're increasing on that interval. So maybe something like this. Okay, we can't have any hills or valleys in here because we know that the derivative is always positive on this interval. We always have to have a positive tangent line, positive sloping tangent line. So we have f of x is increasing on the interval -3 to 2 since the derivative is greater than 0. So that's our first statement. Okay, is that we need to take the information about the derivative, relate it back to the function. Positive derivative means the function is increasing. So we make a conclusion about the function, and here's our justification for that conclusion. And then you can probably guess what I'm going to say next. And I'm going to deal with this information now. And so in a similar fashion, I'm going to say f of x is decreasing from 2 to 5 since the derivative is negative. So it might look something like that. Again, it's got to be decreasing the whole way. We can't have any hills and valleys in here because of the statements decreasing over the entire interval. That's what's implied there. So again, we have a conclusion on this interval. It's decreasing. Function is decreasing. And a justification because the derivative is negative. So after you have these two statements, then you can say what type of extrema is found right here. So we can plainly see what it is. It's a maximum. So we can say, therefore, there is an absolute maximum on -3 to 5. Okay. Just a quick comment here on my graphs. I know I don't have endpoints, big circles, dots that are colored in like we typically would have, but it's because of the notation here of the interval, the square brackets, we know that those points, it's continuous all the way to those endpoints. Okay, so let's take a look at this example. It says, what absolute maximum value? So now we actually have a function. So we're going to have to do something using some algebraic manipulation. What absolute maximum value of the function f of x equals x cubed minus 3x squared plus 12 on the closed interval from -2 to 4. Okay, and at what value of x does it occur? So this is a no calculator, so you can't graph it. So we have to use the process that we outlined just a little bit earlier. And so we're going to take a look at the derivative. We have to go on the interior of this interval, and we have to find cusps and corners and hills and valleys, all of those places where we have critical points. So we need the derivative here. So the derivative is 3x squared minus 6x. We're going to set it equal to 0. And I know I've said this several times now. Once we find the derivative and set it equal to 0, the steps are predetermined. We're going to factor and solve. Okay, so we're going to factor this, and then we're going to solve it. We got a factor of 3x. We'll set that equal to 0. We get x equals 0. Got another factor, x minus 2. Set that equal to 0. Solve, and we get x equals 2. So we have hills and valleys at these locations. Not quite sure which one's which. We look at the derivative. It's defined everywhere. It's a polynomial, right? Just like this was a polynomial. Differentiate it, we get another polynomial. It just is a quadratic instead of a cubic. It's defined everywhere, so there's no cusps and corners, no undefined derivative. So we can just fly right past that and make our table for our candidate with our candidates in it. So here's 0 and 2, right? Those are the hills and the valleys. Again, we're not quite sure which one's a hill and which one's a valley. And then here are my endpoints, -2 and 4. And so now it's a matter of finding all the function values. So we are going to just from top to bottom, we're going to remember this is really critical. We got to plug this back into the function. We're done with the derivative now. The derivative found us the hills and valleys. Okay, we're coming back to the function because we want to know the value of the absolute maximum. Okay, so we are cranking this out here. We're plugging in -2 and getting -8, sticking it in the table. Plugging in 0, getting 12, right? 0, 0, 12, sticking it in the table. Plugging in 2, getting 8, sticking it in the table. Plugging in 4, getting something greater than 12. Okay, so we know that this is the location of the absolute maximum. Now we're also being asked what is the absolute maximum. So we actually do have to do the math here, right? So we've got 64 minus 48 plus 12. So that looks to be 28. And so we know that the absolute maximum then is 28. And so I've written a conclusion here that f of 4 equals 28 is the global maximum by the candidates test and occurs at x equals 4. So notice I've answered the question. I've given my justification, and this is kind of a nice thing. It just says by the candidates test. So that's my justification. My justification is that they can plainly see the table and see that I have tested candidates. And then my location as to where the maximum occurred. Okay, so when we get back into the classroom, then we'll go over the takeaway from the notes, and we'll apply this to our practice questions.